you have 25 minutes, but 1 minute for preaching.
So, thank you, Chairman. So, first of all, I'd like to start by thanking the organizers for giving me this opportunity to present my work here. Well, today I will not be presenting about the small grains which Mr. Shanenko was talking about. I'll be talking about something which is called as matching effects, and this we did in a superconducting film which has got an array of holes. We were trying to look at the origin of these matching effects in these systems. So, let me thank the collaborators who have essentially worked in this project. So, Sanjeev Kumar was the postdoc in my group who has done most of the experiments. He was initially assisted by a master's student. And then later Pranna joined the group as a PhD student, and she helped in making some of the devices. John and Vibhas are working in Pratap's group in the Tata Institute, and they helped in making some of the natrium nitride samples. Okay. So when we talk about matching effects, the first observation of matching effects was seen in such networks, such wire networks, superconducting wire networks. They were done in different geometries, either in square lattices or Kagome lattices. The essential point is that the width of the superconductor was of the order of the coherence length. And what was observed is that if you make a resistance measurement of these wire networks as a function of magnetic fields, you start observing oscillations in the resistance. And the period of these oscillations is proportional to a flux quantum. And this is what was referred to as the matching effect. In addition, you also see oscillations in TC. However, these oscillations, this effect is a very, very small effect. Now, the explanation of this matching effect which was observed in these networks comes from the little Parkes effect, which is evident in a single thin-walled superconducting cylinder, and it just comes from the oscillation of the superconducting kinetic energy. And this gives rise to these oscillations in TC. However, little Parkes effect is seen in a single superconducting thin-walled superconductor. So now people wanted to understand that why such matching effects are also observed when you move to multiply connected wires. And the answer was obtained from some theoretical calculations which incorporated in quantum interference effects. So what they did is that they calculated, so the quantum interference effects was arising because of the summation of all the closed paths the electrons can take around the underlying lattice. And people did these calculations around different lattices. And what they noticed is that in addition to the strong period which I spoke about, that the period proportional to a flux quantum, you start seeing finer structures. So this is the classic signal of matching effect in a wire network. So you start seeing fractional vorticity. Now people later also did experiments in superconducting films which had these arrays of periodic holes. And they again did it on different geometries which were synthesized by e-beam lithography. And if they, of course, here they were much larger structures. The superconducting width between the holes were not of the order of the coherence length. And when they measured the resistance of these systems, they also observed similar effects. The effect was exactly the same. When you measure the resistance as a function of magnetic field, you start seeing oscillations in the resistance, and the oscillation period is exactly proportional to that of a flux quantum. So there was an alternative explanation given to this kind of a system. And the explanation comes from commensurate pinning. So it was said that when an integer number of vortices gets trapped in each of these holes, then you have the vortex lattice which becomes commensurate with the underlying antidot lattice, and then you start getting matching effects. So at the matching fields, there is maximum pinning, so your critical currents will be enhanced, and hence the magnetoresistance will show a minimum. So in this kind of a model, there are two sources of pinning. First, of course, these holes act as a potential well. The height of the potential well is proportional to the condensation energy. So when you increase the magnetic field, what will happen is this height of the potential well will only decrease. So the potential will become more shallower, and you will just get a monotonic variation with magnetic field. So the pinning will just vary monotonically with the magnetic field. It will not give rise to any oscillatory behavior or the matching effects which we see. However, if we include the intervortex repulsive interaction, then this will lead to this oscillatory behavior. Why does that happen? Because at the matching fields, each vortex will lie in a cage which will be isotropically surrounded by the 6 neighboring vortices, which will happen in an hexagonal lattice, and you will have commensurate pinning such that you will have maximum pinning at these matching fields, and you will have resistance drops. So between the two scenarios, that is between quantum interference and commensurate pinning, the main difference which lies is that in quantum interference effects, you will have both thermodynamic as well as dynamic quantities should show the matching effect, while in commensurate pinning, which is related with the motion of the flux, should show up only in the dynamical quantities. So you should not see any matching effect in any thermodynamic quantities. So the motivation of taking up this project comes from the literature. So as I said, people have done these studies in these kind of systems, and you would see that a very similar kind of systems, like these were samples of superconducting niobium which had these antidotes, and the size of the antidotes was about 25 nanometer and 30 nanometer in this case, and the explanations were completely different. So in these they were explained through commensurate pinning, while in this they were explained by quantum interference effects. So they were varied opinions. So we wanted to address this controversy, and to address this controversy we had different tools. So first what we wanted to do is that we wanted to see what is the effect of matching effect on the interpore separation. So if you change the interpore separation, how should the matching effects change? We also wanted to vary the disorder of the superconducting films, because the disorder of the superconducting films would change the superconducting properties like the coherence length and the penetration depth, which would in turn able to tune the intervortex interaction. And the more important thing was that we wanted to use a different experimental tool. As I said, that most matching effects were studied by conventional transport measurements. So people used to see these oscillations in the resistance. We wanted to use a different technique to probe this, and the motivation will come in a short time. So a little bit on the samples. So the samples which were synthesized is that we used predefined templates. So the template was nothing but a membrane of aluminium oxide, and in these templates you had predefined pores which were perfectly ordered in a hexagonal arrangement. So we used templates of different pore diameters, one in which the pore diameter was 35 nanometer and the other in which it was 18 nanometer, and consequently the pore period was also different in the two cases. And on top of that, we deposited a superconducting niobium nitride. The superconductor which we were using was niobium nitride in this case. So the system which we have is this. We have this superconducting film, and you have these periodic area holes. And you can see the film has got deposited only along the walls of these holes. A little bit about why we chose niobium nitride. So niobium nitride is a very nice system where you can actually tune disorder very easily. So you can just change the niobium vacancies in these systems, and you can change the disorder of these films. Now with the least disorder film, you get the bulk TC, which is around 16 Kelvin. If you make the films more disordered, more niobium vacancies, you reduce the TC and you disorder the films. So we have a handle on changing the TC of these systems. Interestingly, if you measure the superconducting parameters as a function of disorder, the coherence length does not change much. If you see this blue line, the coherence length changes from around 5 nanometer, shows a small dip, and then it increases to about 7 nanometer. So the coherence length does not change much with increase of disorder or decrease of TC. But interestingly, you have the penetration depth. If you do a measurement of the penetration depth almost changes by an order of magnitude. So if you take the penetration depth of your least disordered film, which has got the maximum TC, it is around 200 nanometer, and it shoots up by almost orders of magnitude when you make the films more disordered. So this really will help to tune the intervortex interaction. So as I said that there was, so most earlier experiments were done by the transport measurements. The transport measurements, one limitation was that when you study matching effects, you are restricted only to this transition region, because that's where you want to see, you have only signal over here and you want to see an oscillation over this signal. So you don't know what is happening deep in the superconducting state. Okay, so most measurements were confined very close to the transition temperature. Okay, so what we did is that we used a different measurement. It was just based on a mutual inductance technique. So you have two different coils, a primary quadrupole coil and a dipole or secondary coil, and we sandwich the film in between the two coils. So as soon as the shielding currents develop, you will have a drop in the splitting response, and that is what we use to measure the matching effects. So this is just a picture of the main probe which we use. So what we see is that this is the real part of the mutual inductance and this is the imaginary part. So you see that as soon as the film is becoming superconducting, you have a drop in the mutual inductance signal. And now you can see that here we have sufficient signal to see what is happening to the matching effects deep in the superconducting state. So a little bit about our samples. So we did these studies on various samples, and how did we name them? So we named it, as you see, there's S1812. This 18 stands for the pore diameter, the diameter of the template which we have used, and this is the TC. So as I said, the TC is a measure of the disorder of the films. So we changed the disorder of the films and we did experiments on two different pore diameters. We also checked that the TC which we measured by a mutual inductance technique matches with the one which we measure by magnetoresistance, and it matches quite well with the zero resistance. Okay. So now we did the mutual inductance measurement as a function of magnetic field, and there you are. This is a measurement which is done on a sample which is has got 18 nanometer pore and a TC of 4 Kelvin, and you can see these oscillations with magnetic field. Before I show the results for all my samples, we wanted to convince ourselves that we are working in the linear response regime. That is, your AC drive field is small enough so that we are not nucleating any additional vortices. So, if the AC drive field is quite small, then what it will do is just compress or relax the vortex lattice without any additional nucleation of vortices. But in the nonlinear regime, you will start nucleating additional vortices in the antidots, and then the entire premise of commensurate healing will fail. So we checked whether we are in the linear response regime, and what we saw is that when you increase the current beyond, say, 4 milliampere, you start getting additional effects. So we try to measure always at very low currents so that we are always in the linear response regime. Similarly with the frequency dependence, so we try to keep the frequency of the AC drive at 60 kHz, which was again in the linear response. So now is the result for the matching effect for all our samples. So you see these oscillations. This is the sample for a 35 nanometer pore diameter, and you can see 4 periods in this sample, while in the sample with an 80 nanometer where you decrease the pore diameter, you see only 2 oscillations. The other important feature which you can see here is that the oscillations survive to much lower temperatures. So all previous measurements, as was done by transport measurements, matching effects was observed only to about 90% of TC. When you see that for a sample which has got the lowest pore diameter and the highest disorder, that is the lowest TC, the matching effect is surviving almost to 10% of TC. So it's really surviving up to the in the superconducting state. Now to find out the matching fields, it's simple. The first matching field is nothing but the flux quantum by the unit cell area. So if you take the unit cell area for your two different systems, that is the one with 35 nanometer and 80 nanometer, it matches well with the first matching field which we have observed. So for a 35 nanometer, it is around 2.1 kiloaustin, and for the 80 nanometer, it is around 8.9 kiloaustin. So this quantity Ns is the maximum number of vortices which you can nucleate into your antidotes, and this, if you incorporate the intervortex repulsive interaction, this number, this expression was worked out, and if you try to work out this for our system, approximately it matches quite well. So for a 35 nanometer system, you should observe 4 periods, and for 80 nanometer, you should observe 2 periods. Interestingly, this expression shows that you should have a temperature variation, because if the coherence length is changing as a function of temperature, the maximum vorticity which you can have should change with temperature. However, we did not observe any temperature dependence in our system. Okay. So we of course compared it with our conventional system, the conventional measurement, that was magnetotransport. On the same kind of films, we made contacts to measure the magnetotransport. And here, of course, you see the oscillations. The oscillations matches with our mutual inductance measurement. But as we had anticipated, this is of course lying to much higher temperature. So this is surviving only to about 70% of Tc. While for a same sample, when we measured it with the mutual inductance technique, it survived to around 10% of Tc. We also measured the critical current of these systems, and we saw these oscillations. So the critical current gets enhanced at the matching fields. So till now what we have seen is that all dynamical quantities show this matching effects. And we wanted to ask ourselves is whether also thermodynamic quantities show this matching effect. For that, we wanted to look at the transition temperature. So what we did is that we measured the temperature dependence of the mutual inductance at different magnetic fields to find out the Tc. So we could get the Tc from here. And here you see that you start seeing the oscillations in Tc. This is the red curve over here. And you see it in all our samples. So these green curves over here show the oscillation in Tc which we observe for all our samples. We also matched it with our magnetoresistance measurement, and here you see the blue one is from mutual inductance, the red one is from magnetoresistance, and we indeed see a oscillation in Tc. Okay. However, the Tc onset was showing was not showing any periodic variations. So now, can there be Tc oscillations in an antidot film? As you remember the second slide which I showed about wire networks, in wire networks, if you have quantum interference effect which comes from the little Parks effect, you should observe Tc oscillations. However, the amplitude of the Tc oscillations are worked out under the Ginzburg-Landau framework, and if you find out that you should also observe oscillations in the Tc. So do our iodine nitride antidot films just behave like wire networks? This was a question which we posed. Now, as I said that if you work out the amplitude of the Tc oscillations from the quantum interference effect, the amplitude of the Tc oscillation should be very tiny, should be just around 30 millikelvin. However, what we observe is a much larger effect. We see oscillations of the order of 800 millikelvin. So this is not really behaving. These anomalous Tc oscillations cannot be explained by the quantum interference effect. Again, we wanted to verify that whether our antidot films can behave like a wire network. If you remember, the first premise is that the superconducting thickness, the thickness of the superconducting film should be of the order of the coherence length. So if we try to find out that for our system, this is valid only very close to Tc. So our systems can behave like a wire network only very close to Tc. but not at very low temperatures. There it is just behaving as a periodic arrangement of units. So then what causes these TC oscillations? So what we feel that this TC what we are measuring is not the real thermodynamic TC. It is just the temperature at which the flux motion sets into play, and it's a temperature at which the flux flow sets in. So this can be explained by a model which is valid in our case. So next what we did is that we measured the superconducting energy gap, and we tried to see whether we also see matching effects in this quantity. For this we prepared tunnel junctions on our template. So you have this niobium nitride film which was deposited on the template, and then we made a niobium nitride, we oxidized it, and then a silver top electrode to form the tunnel junctions. We saw whether this is giving the proper conductance spectra, and this is as a function of temperature, which we did on our system. This behaves like a nice PCS superconductor. So this was, and now what we did is that we measured the tunneling conductance as a function of magnetic field, and this is what was the matching effect. And what we see is that whatever temperature you measure, you don't see any matching effect in the superconducting energy gap. So the tunneling spectra really matches one of the top. So there is no matching effect in the superconducting gap. We wanted to check whether this is within our resolution limit. So what we did is that we changed, suppose we have a 10% change in the gap value, we try to see whether we can measure the difference in the tunneling signal, and we see that there should be a difference in the tunneling conductance, which were not observed in our experiments, which means that truly we are not seeing any oscillations in the superconducting energy gap. So our results indicate that the commensurate pinning is the more dominant feature observed for these matching effects. Of course, we want to do some STM measurements on this to really see the vortex configurations, where the vortices, how the vortices are nucleating in these antidots. These are very, very small structures. Whether we can nucleate vortices between the antidots within the superconducting films or not. And we also wait for simulations to see the vortex configurations. So finally, the summary. So we have observed matching effect in superconductors with an area of holes, and we have seen the dependence of matching effect both on the size of the holes and the disorder of the films. What we have seen is that all dynamical quantities show the matching effects, while true thermodynamic quantities are not showing the matching effects, which says that this is mainly dominated by commensurate pinning, which is due to the enhancement of the vortex-vortex interactions. Thank you for your attention.
Any questions? Sangita, may I ask you why you don't consider critical temperature as the thermodynamic quantity? Because in S-wave superconductors we have direct relation between delta and TC. So I'm a bit confused why critical temperature does not show any signature.
So in these systems, when we are measuring the TC, we are doing it by transport. So you will have a temperature when, it will not be very different. It will not be very different what we are measuring. But in this case, since we are nucleating the vortices, at the particular temperature, you will start moving the vortices. And this will be a more dominant effect, which we think.
Okay. Other questions? Yeah, let's thank again the speaker.